So this one's different than the other ones. It's got a fractional exponent. Okay. So you're going to add 7 to both sides. 2x to the 3 halves equals 54. Divide by 2, divide by 2. X to the 3 halves equals 27. So the mistake here is to just raise both sides to the 2/3 power.
Mhm.
It will work. It works. I believe it works in this one, but it does not always work. And that's why we're looking at it. It works when there's an even number on the bottom. So how to I don't know that I would want to remember that as a student. If you get the other case where there's multiple solutions, you would miss out. So just be aware here. So this is x equals 27 to the 2/3 power, and you have to recognize, oh, 27 is really 3 to the power of 3. So that means that this is 3 to the power of 3 to the 2/3 power. When you have an exponent to an exponent, you multiply. So you're going to multiply 3 times 2/3. That ends up being 2. The 3's cancel. So x equals 3 squared, which equals 9.
Okay.
Okay, so the other variation on this problem, and this is not this is just the way it is. So they put this in the end of course review. X plus 2 to the 2/3 power minus 9 equals 0.
Mhm.
Okay, so now to solve this, you're gonna add 9 to both sides, and you get this x plus 2 to the 2/3 power equals 9. Okay. If you just raise both sides to the 3 halves power, this is the case where you'll have an issue. So this on the left is actually the cube root of x plus 2 squared. And if you're ever like, well, hey, how do I remember that? X to the 1/2 is the square root of x. Well, there's really a 1 there, and there's really a 2 there, and that's the mapping. That's how you figure out where things go. All right.
Okay.
So cube root of x plus 2 squared equals 9. So in our problem, to undo the cube, we use the power of 3. So 9 to the power of 3, 9 times 9 times 9. Maybe you know that's 729. Maybe you have a calculator. But on the left here, x plus 2 squared equals 729. How do you undo a square? This time, though, you have to use a square root. When you use a square root, it's plus or minus the square root of 729. Okay, and I think we actually might have even done this before. This is plus or minus 27.
Mhm.
Square root of 720. So then you have to subtract 2 from both sides. X equals minus 2 plus or minus 27. So there's really two solutions: minus 2 plus 27, minus 2 minus 27. So that's 25 and minus 29. So if we put these problems side by side here, let me grab this one and then I'll write the other one here. The key difference, here's the other one, x plus 2 to the 2/3 power equals 9. The key difference is that when the 2's on the bottom, or an even number more generally, there's only one solution. But when the 2 is on the top, or in this case 3 is on the bottom, or an odd number, there's the potential for 2 solutions.
Mhm.
So that is all I have to say about fractional exponents. I would just look at these examples again before you go into the exam for that. All right. Let's see what else we can do. Even and odd. We have not spent much time on even and odd. I saw that in your notes. How much was that emphasized in the class? Even and odd.
Um, it was pretty heavily emphasized along with like discontinuities and stuff like that. We spent a good chunk of time doing that.
Okay, so we will talk about even and odd and then talk about discontinuities next after that. Okay, so let me give you a function. I'm going to tell you this one is even to start out because it's nice to actually have one that works.
Mhm.
So the fourth, actually, let me put some numbers here. 2 minus 8x to the fourth. Okay, so the first thing you do is you replace x with minus x, and I just immediately write f of minus x, and then wherever you see an x, and I like to do this in parentheses when you're substituting, you put that minus x in for x. All right, and then off to the side here, this is kind of like what we would need to know ahead of time. Minus x to an even power is always x. Minus x to an odd power is always minus x. Okay, so notice the case we have here is the one up top. So this becomes 2x squared minus 8x to the fourth. Is that okay? Is that clear how that came to be?
Yeah, that makes sense.
Okay, and you look at this and you ask yourself, you literally ask yourself, is this the same as the original? It has to be exactly the same. Is it the same as the original? The answer is yes. And that's because it's even. I gave you one that is even. We apply this f of minus x, you get something that looks exactly like the original. If the answer is no, you go and do something else. So we'll do that on the next one here.
Okay.
Okay, so this one is odd. F of x equals x minus 3x cubed plus 5x to the fifth. And it's the same approach. You wouldn't be told that it's odd, but you have to, I'm telling you this, but you wouldn't know that in advance. But you try this f of minus x. So minus x minus 3 minus x cubed plus 5 minus x to the fifth.
Okay.
Okay, now there is an exponent here. It's 1. Again, if you have minus x to an odd exponent, it's minus x. So this first one becomes minus x minus 3, and then the net result of this is the negative. It becomes minus x cubed.
Okay.
Okay. But really, like, what I want you to do is, I actually don't want you to do that. I want you to see that, okay, this part that I'm boxing in becomes minus x cubed, and then this minus goes with that one. So you get plus 3x cubed. Right, and then the same thing here. This boxed in part becomes minus x to the fifth. It combines with this one right here and becomes minus 5x to the fifth.
Okay.
So now you ask yourself, because you don't know whether it's even or odd, you ask yourself, is this exactly the same as the original? And the answer is no, this is not the same as the original. Okay, so then what do? You factor out -1 from everything. So you put a negative or -1 on the outside. All it does is change the sign of what's inside. So it's x minus 3x cubed plus 5x to the fifth. Then you ask yourself, is this the same as the original? Now in your notes, it might say f of x, but I mean, that's what we started with.
Mhm.
Is it exactly the same? Not the minus, the part inside parentheses. Is the part inside parentheses exactly the same as the original?
Yes.
Yes. So that when you get a yes there, that means it's odd.
Okay.
So now we're going to look at some functions that are neither even nor odd, and most functions are neither. So this, I mean, the realistic, in terms of like like in real life, like most of these are not even or odd. So it's that's the way it goes. So here's one here. Let's say f of x equals x squared minus 1. So your process is you first figure out what is f of minus x. Okay, and that is x squared minus 1. Is that the same as the original?
Yes.
Yes, so this is even.
Okay.
But it's not that hard actually to make it into one that does not work. So let's do that now here. Sorry, I meant to give you one that didn't work. Let's go x squared minus 3x. So we'll first find f of minus x. So that's your minus x squared minus 3 times minus x. So this first one becomes x squared minus x times that becomes plus 3x. And this is definitely not the same as the original. And that's okay. That just means it's not even.
Okay.
Might be odd. We don't know yet. So you factor out -1. I think more importantly is to say you change the sign. This one's positive. So you change the sign of everything. And it's kind of odd, but or it's kind of strange to look at it like this, but that is the procedure. Okay. And you say, ask yourself the same thing. Is this part inside parentheses, is it the same as the original? And the answer is no, it is not the same. So that means it's not odd.
Okay.
And I'm trying to think of a good like analogy here, but the only thing I come up with is that it like at this point, you know that it is neither even nor odd, and you don't have to go any further. Because if it's not even and it's not odd, well then it's neither. There's no other possibility.
And that's how you write that, just neither even or odd.
You just say neither. They usually
Okay.
are like, all right, just write neither.
Okay.
Now your chapter review covers other functions. Did you like it's got some problems in here, like let me see if I can get this. Like here's a problem. It went y equals 3x squared minus 4 absolute value of x.
Yeah, I think we did a little bit of that.
Okay, so it's the same approach, and we'll just change this to f of x. We'll just review some stuff here. So f of minus x. So you're plugging in minus x for x. Wherever you see an x, put it in parentheses. If it's in absolute value, you can put it in parentheses, but we're going to drop it here in a moment. So minus x squared becomes just x squared. The absolute value of negative x is x. The absolute value always returns positive. So this part right here becomes x.
Okay.
So the question is this even? Is this exactly the same as the original?
Does this like, does the absolute value have to be there?
So this is like this is kind of an exception to what I'm saying is this. So the answer is that let me do it this way. We can't tell. We can't use this. So you have a calculator and so do I. I want to show you how to graph absolute value if you don't already know. Do you know how to graph absolute value?
Not really.
Okay, so let me new share my calculator and I'm going to go to y equals, I'm going to clear this out. I'm going to do 3x squared minus 4. And then let me know when you get up to this part, because this is where some different button presses.
Okay, so okay.
Okay, so under math, this math button, if you hit that, there are these math functions. You can see like cube, cube root, x root, and absolute value is not there. Sorry, there it is. It's under num. I don't know why, but it's under num. Okay, so we hit enter. Yours may actually have like an nice absolute value. Mine does not. And then you put the variable in there like that. So the before you graph, do a zoom standard. Just will help you to get it to look like that. So another way to know if a function is even or odd is the type of symmetry that it has. So an even function, I'm writing this down, it has what is called y-axis symmetry. It's like looking into a mirror and seeing yourself. It's not like those weird mirror problems we were doing in physics where the image was like virtual and upright. Like, no, it's like, does it look the same left and right? Now, if you need to, you can zoom in here. I'm going to just zoom in a tiny bit here to kind of further this point. But like, to me, it's pretty solid that this is even. But sometimes it's worth just zooming in just to see like, yeah, it's exactly the same. Yep, goes down, comes up. Like, I'm convinced. Okay. So the strategies that we've been using, they work until you get kind of things that you don't know how to handle. And we'll look at another one here. Let's go do a new share, go back to my other screen. So the absolute values under num, nun, num, and that you may end up using that again. So here's another one. Let's say f of x equals sine x minus x cubed. Okay. Now, if we do the approach that Matthew's been talking about, okay, we're going to put in minus x for x. You know, I'm feeling really good. And then it's like, well, what is sine minus x? You know, I'm not sure. And then, but over here on the right, you're like, all right, well, it becomes minus x cubed. That goes with that, so it becomes plus x cubed. Okay. So I want you to graph this. I'm sorry, I want you to graph this one. And I want you to tell me what you see when you graph it. Oh, and your calculator should be in radians, not degrees. And if you're not sure how to do that, let me know. I'll help you talk you through that. What do you see, or have you been able to get it graphed yet?
Yes.
Okay. Let me new share my graph and tell me if you got something similar. So here's the graph. Looks like it goes kind of down, comes down, but something's going on there at the origin that we can't really tell. So this is a good time to zoom in. So I'm gonna do a change my window here. I'm gonna go like -2 to 2, and then I'll go -2 to 2 again. And we'll just graph. And if it doesn't look right, you just change your window again.
Okay.
All right, so let me know if you get something that looks like my screen there. And then I'm gonna go back and share the other screen. So this function is considered odd, and it has what's called origin symmetry. And what that is it's a rotation about the origin, about 0, 0. So the idea is that if you were to just take this top half here and you were to rotate it 180 degrees, it would look like, or they would look like the bottom half. And same way, like if you were to take this and rotate it 180 degrees, it would look like the other half.
Okay.
So what's very important is that it can only have one. It's either even, or it's odd, or it's neither. So it never has both. It's not like it's even and odd or odd and either. The odd one I think is a little bit more difficult to see because it's really got to have, you really got to be able to rotate it visually and see that on there. All right, so I mean, so the truth is like like what I would give you as a student is I'm hoping you would get something like these where you just put in f of negative x. But the reality is that you could get absolute value, you can get trig functions, you can get exponential functions. And with those, you either have to know the properties or you just graph it and see what it looks like.
Okay.
Did you have to find any formulas for inverses, or was it just like, no, that you didn't say that, never mind. Okay, let's go to discontinuities. So let me grab a question here to start us off. So question 19 from your chapter review, it says, is the function continuous at x equals 0? So there are a couple of different types of discontinuities. There are vertical asymptotes. There are what are called jumps. And the third one is what are called holes. Only the first two are not removable, but the third one is. This is what's called a removable discontinuity. All right, but they all sort of happen for the same issue, is that they all are sort of caused by what, division by 0. So when you put 0 in for x, well, what happens here? You get 0 squared minus 3 over 0 plus 2, which is minus 3 over 2. Are you dividing by 0 in this?
No.
No, you're okay. But let's look at another problem. You'll see how this happens. Okay. So when you put 0 in for x, what happens? Well, you get 0 over 0 squared minus 2 times 0. 0 over 0 minus 0 becomes 0 over 0. So it's not the 0 in the numerator that's a problem. This is okay. This one's okay. It's the 0 in the bottom that is very bad. This is bad, very bad. Okay. So I want you to graph this in your calculator. And I'll be right behind you to graph it as well.
Graph the
original function.
original.
Yeah. Oh, and when you're graphing it, please put parentheses in the denominator. Super, super important, because your calculator doesn't know, and then it just ends up creating a lot of problems when you graph it. So, and if you're not sure, just add them in the top and the bottom. Will not hurt you.
Okay.
Do a zoom standard. Let me know when you get yours up, and then I'll share my screen.
I have mine.
Okay. You share. Okay, so this screen, this is one of the limitations of the calculator. Like, it's almost like they're connected, but they're not. So you can't get around this. Like, this is just a issue with the calculator, but that's a division by 0 error or thing there. So that's a vertical asymptote. All right. And that occurs because when you put 0 in, you get 0 in the bottom,
Mhm.
right? But this one actually has more than that. Now, how much did you talk about discontinuities? Like, were you talking about how to fix them? Were you talking about like just how to graph them? What was the nature of the discussion on discontinuities?
I think it was mostly how to graph them because we went over the different types of them.
Yeah, and that's what I've done. I've gone over just, hey, here are the different types. Okay. Let's see here. Because this you're going to do this again later in the course, so it's kind of odd that you would do it again here. But okay, no big deal. All right, so let me go back to the other screen. Okay, so let's say I asked you to graph y equals x squared minus 5x minus 6 over x minus 6. So I want you to graph this in your calculator, and I've kind of helped here, but you might as well put the numerator in parentheses as well, just to be kind of careful there. But I want you to graph this and tell me what I want you to use one word to describe the graph, and believe me, you'll be able to when you get this.
Okay. Oh, um, it's a diagonal line.
It's a line. Okay, now if you and you're going to see this in a moment here. So it's diagonal line. It goes through one, right, like this. It looks something like this. Okay,
Mhm.
but the problem is this graph is wrong. You're like, how can it be wrong? It looks right on my screen. So if you're still seeing my screen with the graph that I'm drawing here.
Mhm.
Okay, so if you factor the numerator and you factor the denominator, which there's nothing to do here, do you see how these cancel?
Yes.
So where they cancel, which in this case is at x equals 6, because 6 is what makes it 0. That's where there's a hole. Now you do this later in the course. You're in pre-calculus, is that right?
Mhm.
Yeah, I mean, you're going to see this later on. So I'm just not sure what to say here, but you would, if you were to very slowly trace along your graph, you would see that there's a hole there. So let me do this. I'm going to just share another screen here. Okay, so I'm gonna graph the same thing here because I want you to see what happens here. And because it's a little bit hard on your calculator, but if you were to actually go over to 6 right here, you can see how it says undefined right there. If you're seeing my screen.
Mhm.
Yeah, so that, like, the calculator knows that it's undefined. Yours would throw up an error. Like if you tried to get the value at 6, it would say, I don't know what to do. So now the other type of problem you might see is the flip of this. It would be x minus 6 on the top, x squared minus 5x minus 6. This one's different. It's like, well, wait, what's going on here? This one has a vertical asymptote, and the reason is because this factors into, let me just show you right here. It factors into, same thing as before. x minus 6 up top, x minus 6, x minus 1. So the x minus 6's cancel.
Mhm.
So instead of just deleting them, I'm going to put a 1 here and a 1 there. And you can see that it's, no, I'm sorry, why did it do that? Because there's a +1. Sorry, there we go. See how they're exactly the same. So that this is the second one is the reduced form of the previous one, but it still shows the same behavior. But if we go back and look at the line example, the line doesn't show the behavior. It just shows, hey, I got a straight line. So you have any other more insight into what type of questions you're going to be asked on discontinuities?
Let's see.
Because I'm looking at your notes here. Your notes say removable discontinuity. We talked about that at jump. You can't remove. Infinite discontinuity is an asymptote. This is moving into calculus concepts, but I guess they felt like this was a good place to cover it. That review packet you sent me, I didn't see any discontinuity questions on there. Did you get a continuity question on your diagnostic?
Yeah, there was like a page of it where it was like, what does it mean if a function has a discontinuity? Describe how discontinuities can be found above the function and how they're represented on a graph, and then find the end behavior and describe how it's determined.
Okay, well that's a lot there. Do you happen to have a picture of that?
Yeah, I can send a picture.
Okay, please, either a text or email on that.
Okay. And then for some of the questions, I didn't really know, to be honest.
That's okay. I just, it gives me a feel for like what to give you as problems here, because I want to replicate as much as I can. All right, thank you. You sent that over. Perfect. Yes. All right. Okay, so here's what we'll do. We'll just answer the same questions, but I'll give you a different function. How about that?
Okay.
So let's say f of x equals x plus 2, x minus 2 over x minus 3, x plus 1. Okay, so part A has nothing to do with the function. It just says, in general, what does it mean if a function has a discontinuity? So this is where you go right back to your notes, the notes that you sent me, and you somehow regurgitate, you know, exactly what your instructor asked you to write down. The instructor wants to know that, number one, you wrote it down, and then number two, like, did you actually understand it? Can you convey it in a few sentences? So that's what they're looking for here. I like lists, so I would say 1, vertical asymptote, 2, jumps, 3, holes. I would talk about what they are, and then I would say what they mean is that at that point, the function is undefined.
Okay.
But that has nothing to do with this function. Like they'll probably ask you that again on that. Describe how the discontinuities can be found for the above function. Okay, so to do part B, you're first looking for, and I wish I knew for sure, if you're looking first for, are there any cancellations? Because cancellations lead to what are called holes. It would have to be exactly the same on the top and the bottom. This one has none. There are no cancellations.
Mhm.
So then the second thing you look for is where the denominator is equal to 0. So you literally set the bottom equal to 0. And
Okay.
since it's already factored, you're really pleased. You're like, okay, I can do this really fast. X equals 3, X equals -1. That's where the function is undefined because you cannot divide by 0. Cannot divide by 0. Super important. Okay. And the denominator equals 0, that corresponds to vertical asymptotes. And the nice thing is that these equations down here, they are the equations of the line of the vertical asymptotes. X equals -1 and X equals 3. So like if you were to graph this thing up here, you would see at X equals 3 and X equals -1, the vertical asymptotes.
Mhm.
All right. So let's see, what is the next question? Give the end behavior of the function. The end behavior of the function. So to do that, you really should graph it. Do you know if you were allowed to graph the one on that diagnostic?
We didn't have a calculator on the diagnostic.
Okay. So let me change this slightly. Let me put a 3 here because that's the way it's given in the exam diagnostic thing. So so the end behavior, it depends on what's called the degree of the numerator and then the degree of the denominator. So the degree of the numerator is squared because it's if you were to FOIL this, you would have a squared on the top. Do you kind of see that? Do you agree with that?
Mhm.
Same thing on the bottom. So when these are the same, you look at the ratio of the leading terms. So the ratio of leading terms is this 3/1, and that's what's called your horizontal asymptote.
Wait, what is? Sorry.
The ratio of these leading terms, these numbers, when you have the same degree, and I'm cautious here to go into much more detail other than to say it's the leading number because you will get to this later in the course. I don't even know why it's being brought up here, but you just look at this first part. And that's your end behavior. So we don't know what the graph looks like. It does a lot of stuff, but we know that when it gets to the end, it approaches this 3 value. So your end behavior as X goes to infinity, Y goes to 3. As X goes to -infinity, Y goes to 3. It's the ratio of these numbers. And I'll give you another example here in a moment, but okay, so let me give you another problem here. So let's say f of X equals -4/2, and this is X -1, X +1, X +2, X -3. Okay, so the end behavior.
Oh wait, it's stuck on Desmos on my end.
Oh boy. Okay. Please tell me. I've been on the other screen for a while.
Oh, I've been writing down.
Okay,
everything.
good. Okay. Well, what I was trying to show you here, it's just this leading coefficient here. So the end behavior is just this. So you know, as X goes to infinity, Y goes to -4/2, which is -2. As X goes to -infinity, Y goes to -2. There is more to it, but we can, for this problem type, go with that.
Okay. Okay.
All right, now the last part of this says, this is part D, it says to find the zeros or the x-intercepts, they're the same. Okay, so let's go back to the one that I gave you. Let me grab this. Let me grab this up here. Okay, so to find the zeros or the x-intercepts, you set the numerator equal to 0. So that 3 comes with it. So you can just say 3, x plus 2, x minus 2, set it equal to 0.
Mhm.
And then the 3 doesn't factor in, but the x plus 2 you set equal to 0, and the x minus 2 you set equal to 0. So x equals minus 2, x equals positive 2.
Okay.
So not to be confused with what we did in part B, which you set the denominator equal to 0. So for discontinuities, for vertical asymptotes, you set the denominator equal to 0. But for the zeros, you set the numerator equal to 0.
Mhm.
And that's the distinction. The horizontal asymptote or the end behavior is this leading numbers stuff.
Okay.
It's kind of a couple things to remember there. All right, so let's try another problem here. I'll have you work out some of this on your own. So let's go with y equals, let's go 6 x minus 3, x plus 1, negative 2, x plus 2, x minus 2. So the first thing I want you to do is tell me where the vertical asymptotes are. I want the equations of the vertical asymptotes, please. Do you have the vertical asymptotes for me?
Just to clarify, the vertical asymptotes are when you take like the x minus 3 and set it to 0, right?
It's the bottom that you set equal to 0.
Oh, the bottom. Okay.
Yeah, and that's what's confusing is like, was the bottom is the top? You got to just have that down. It's the bottom.
And then is like horizontal at the top.
The zeros, the intercepts are the top.
Oh, okay.
Yeah. So give me the equations of those whenever you've got them.
Is it -2 and 2?
Yes, and it's written this way. You would want to write x equals -2, x equals 2, those are the vertical asymptotes. You want to make it very clear that that's what they are. So now,
Okay.
now we can do, we're going to do this out of order because I think this is easier. We can ask where the x-intercepts or the zeros, and that's where the top, you're setting the top equal to 0.
Okay. And that's the x minus 3, x plus 1, right?
Yes, exactly.
Okay. Three and -1.
Yes, perfect. 3, 0, -1, 0, perfect. And then part C is your end behavior. And it really comes down to if we think that the way that this is presented is the way we're going to see it in the quiz, it's just going to be the ratio of those leading numbers. So let me bring that down here. So it's these numbers right here. It's as x goes to infinity, y goes to 6 over -2, but you want to reduce that to -3. And it's the same in both directions. It's the same. The vertical asymptote is the same.
Okay.
All right. Anything else I can answer for you?
I actually don't think so. I think he answered all my questions.
Is the quiz tomorrow?
Yes.
Is it what period is your quiz? Is it
It's 6th period.
6th period? Okay. I know it's not exciting, but maybe at lunchtime, if you got a few moments, just look over the notes and
Yeah.
just refresh. It could make the difference.
Yes.
All right. Well, thank you so much, Julia, for scheduling. I will see you next time.
Okay. Thank you so much.
You're welcome. Bye now.